This is the sixth part in our introduction to pseudospectral methods. In the previous part, we looked at Chebyshev polynomials, and so here let's apply those polynomials to actually interpolating a function. And we're going to drop the time dependence for convenience, and then we can see that uj is, and we're going to denote tnj to be the nth Chebyshev polynomial of the first kind evaluated at position xj. So that gives us this uj as the sum of cn tnj. This thing defines a matrix vector multiplication where the matrix, where u is equal to t transpose times vector c, where the matrix tnj on row n and column j gives us the nth Chebyshev polynomial evaluated at the jth grid point. So on the roots grid, we have the elements tnj is equal to cosine n theta j, or cosine pi n j plus a half all divided by n. And on the extrema grid, it's cosine pi n j divided by n minus 1. So this is illustrated here on the right, where vector u is matrix t transpose times column times vector c. So if we have, so u0 is t0 c0 plus t1 c1 plus t2 c2 plus t3 c3, and similarly for the other points u. Then given matrix t and vector u, we can solve for c if desired by inversion. So let's apply this to see how well the Chebyshev basis approximates a function, and we'll use the famous Runge function, simply 1 over 1 plus 25x squared, and we'll look at the interpolation for 9 points on the roots grid, the extrema grid, and a uniform grid. Okay, so before we start, let's look at some boilerplate that we use in this example and later examples. So we're going to use numpy and matplotlib as usual. numpy.polynomial.chebyshev as cheb will give us access to a bunch of useful Chebyshev polynomial functions. And then there's also scipy.fft has fft, ifft, and the discrete cosine transform and inverses. Our Runge function is defined here, and then we have this function ChebyTerp, which will effectively, given c, it will evaluate u at a given x location. So it's basically going to do this, a dot product between this t and the c's, given c and a given x location or locations. So that's a little convenience function. And this Cheb-Vander effectively gives us t transpose. So this Cheb-Vander function gives us this matrix t transpose. So that's convenient. Then xx and uu are just lots of grid points x, and we'll evaluate that for plotting. So here's some function to actually look at the interpolation with the result on the right. So we have here the roots grid using option 1, where we do a direct calculation, so you can see how we're actually computing this function and inverting it in detail. And then the second option is just using the built-in functions, which of course is fast, just can be done in one line of code. We'll do that for the roots grid and for the extrema grid and a uniform grid. On the uniform grid, we'll just use polyfit to fit the polynomial to the given grid. Okay, so on the roots grid, using a direct calculation here, we compute this matrix T, initialize it to zeros, and then we fill in each element using this definition that we saw right here. So roots grid, cosine pi n j plus a half over n, cosine pi n j plus a half divided by n. Then if we, given the points, if we're fitting a polynomial, we need to have both the x and y points to fit to. And so we have the Runge function at the grid points. This is UCR. and then we invert T transpose, multiply it by U to get the corresponding coefficients on the roots grid. So this little bit of code effectively solves for this array C right here. And then once we have C and T, we can evaluate this summation for all the intermediate points to find U everywhere and see how that does. And so we can see this blue curve is evaluating the range function everywhere when we've interpolated using just 9 grid points. And so you can see how well it does or doesn't do. It's not perfect with only 9 points. We do the same thing using the extrema grid. So the main difference here is that we change the grid points, so cosine pi nj over n minus 1. And then it gives basically the same results. I mean, they're different, but they give similar errors, similar kind of shape. And by contrast, when we use a uniform grid, we get really bad results, especially near the boundaries. And this large deviation here is the well-known range function, range error, range phenomena. If you increase the grid spacing, it gets worse, not better. So you'll get bigger and bigger spikes as the grid points get, as you use a finer uniform grid. In contrast, the roots grid and the extrema grid give convergence as you increase the number of points. So this is the result with 19 points, not showing the uniform grid, just so that it will fit on the page. But you can see how the roots grid and the extrema grid, there's not really a good argument in terms of interpolation for using one over the other. And the clustering at the edges all but kills off any sort of range phenomena. Okay, now we can relate, we could do all of this if we're just looking at interpolation. We can do it explicitly as shown, but we can relate these functions to the discrete cosine transform, and we'll do that here on the roots grid and then also show it on the extrema grid. So we can compute the coefficients, the CNs, by relating it to the discrete cosine transform. And the FFT libraries include these: scipy.fft.discrete cosine transform DCT and IDCT. There's a whole bunch of cosine transform variations. I include a link to the Wikipedia article that lists them out. The type 2 transform, there's lots of type 1s and 2s, etc. floating around in this, and it's a pain. The type 2 transform corresponds to Chebyshev interpolation on the roots grid, which is what we want. And so this is the discrete cosine transform. So I'm not calling it C, I'm calling it A because it's not C. It's almost C. See, if you just erase that little line, you get a C, but it's not quite there yet. And then the inverse transform is shown. And so we have, in both cases, the cosine term is the same. It's cosine pi n over n j plus a half, cosine pi n over n j plus a half. The only difference is in the discrete cosine transform, the sum is over j, and in the inverse transform, the sum is over n. Okay. Also, the inverse transform has this a plopped outside of the summation. This is what's coded in SciPy. On Wikipedia, the type 2 transform has this factor of 2, actually shows up on the inverse transform. So you have to watch out for the definitions. Any library that you're using, you need to make sure you understand what it's actually computing before you use it. Now, we can incorporate this leading term when n is 0, cosine 0 is 1, so we can incorporate this leading term into the summation. But if we do that, then we've got this factor 1/2 that doesn't show up here. So we just define this convenience parameter p, and when n is 0, p takes the value of 1/2, and for all other n's, p is just 1. So now we have this preferred form of this inverse discrete cosine transform right here. And now we can see, if we look at the Chebyshev interpolation on the roots grid, okay, using the Chebyshev polynomials, we can compare that to this inverse discrete cosine transform, and we can see, oh, these look almost the same. So if we can see that they're the same if the coefficients Cn are equal to an times p divided by big N. Okay, so in summary, our function here is Cn like we've been using, and here I'm indicating the comma r that we're on the roots grid. Okay, for these equations we're on the roots grid, where Cn is equal to an p2 over n, so I need to fix that notation. That's p type 2 here. Again, where the p type 2 is 1/2 when n is 0 and 1 otherwise. And then where the a come from this discrete cosine transform type 2, and the u are the inverse of the a. So this is kind of our nice little summary for doing the interpolation using the discrete cosine transforms, meaning the goal is once we have the u, if we have u and t, we want to evaluate the c's so that we can then interpolate everywhere. So again, on the grid, we know u and x, and we can solve this equation for c so that we can then evaluate this equation everywhere. At least that's what we're doing for interpolation. We'll do something a little different for solving PDEs. Okay, so to solve for the c's then, we don't invert this matrix system anymore because that's slow. Instead, we use these fast cosine transforms where we take the discrete cosine transform of u, then we multiply it by p, divide it by n, that gives us our c. Great. Now, I'll note that when we compute derivatives for doing pseudospectral methods for solving PDEs, we're going to be taking pairs of C inverse and C. And when you do that, the 1 over n factor that shows up, like right here, this 1 over n, is going to cancel with, the 1 over n that shows up in this is going to cancel with a corresponding n factor. And so basically when you convert between the a and the c, you have this factor 1 over n, and that's going to cancel out for us. So we'll take advantage of that later. Okay, so let's show how to do the Runge interpolation using the discrete cosine transform. So here I have n is 17, and we create a grid of points, and then we evaluate on the roots grid, so that's Cheb points 1. And then we evaluate the function there, and then the actual work is shown here. So a is just the discrete cosine transform of u, right there. And then we calculate the p array, which is a bunch of ones except the first element is a half. And then c is just p times a times p over n. That was c is a times p over n, right there. And then we can evaluate the function everywhere by doing this Chebyshev terp with c evaluated at all the lots of 1,000 points. And then plot the thing up, and you can see our original, the points on our roots grid, and the Chebyshev interpolation everywhere. So pretty straightforward, not too bad, in order to compute this interpolation. So the equations in theory can get a little bit hairy, but it's not too hard in practice once you've got this blue set of equations. Nice. Okay, let's do the same thing on the extrema grid, so we'll go through this really quick. The discrete cosine transform on the extrema grid. Now this part is called a type 1 discrete cosine transform instead of a type 2. And so we have, those are listed here. And if you look at the Chebyshev interpolation on the extrema grid, it's given by this. So you can make a comparison between the Chebyshev interpolant and the inverse transform. And when you do that, you can say, oh, Cn then is simply an p1 divided by n minus 1. Done. And then you can do the summary again. So we have this thing noting the comma e because we're on the extrema grid. Then when we say, okay, but C is A times P over n minus 1, where A is the type 1 transform and U is the inverse of that. And then we code it. It looks basically the same, but now we have Cheb points 2. Confusingly, the roots function was Cheb points 1 using a type 2 transform, and the extrema grid is Cheb points 2 using a type 1 transform. Super annoying, but that's what we got. So be careful with these numbers. And then the effort here is you do the discrete cosine transform. Now we have to tell it type equals 1. Before, the type 2 is default, but the type 1, to get that one, we have to tell it, change the default there. We get the P array, and importantly, the P array here is 1/2 for both 0 and n minus 1, and 1 otherwise. So you have to be a little bit careful about that detail. So we have both 0 and n minus 1 is 1/2. And then we do the multiplication. Obviously, this isn't super efficient because most of these you're just doing multiplying by 1s, but we're just trying to illustrate this in as few lines of code as we can. And then you get basically the same kinds of results. Okay, so that concludes this presentation, and then in the next part we'll talk about derivatives and start looking at examples.